A rational function is a function of the form f of x equals p of x over q of x, where p of x and q of x are polynomials and q of x does not equal 0. The domain of a rational function. When a rational function f of x is defined as p of x over q of x, restrictions must be placed on the domain to avoid division by 0. The domain of a rational function includes values of x for which q of x does not equal 0. So let's take a look at this example. Find the domain of the function f of x is equal to the binomial x minus 5 times the binomial x minus 3 times the binomial x minus 2 divided by the product of the binomial x minus 3 and the binomial x plus 4 and the binomial x minus 7. In order to find the domain, we just have to make sure that none of the factors in the denominator are equal to 0 by finding what values of x will make them 0. Well, for this first factor, if x is equal to 3, we get 3 minus 3 is 0. So x equals 3 is a value that I have to exclude from the domain. The next binomial x plus 4 has a 0 of x equals negative 4. So that's another value that I cannot allow x to be. And the last factor, x minus 7, has a 0 of 7, because 7 minus 7 would be 0. The domain of f of x is all real numbers except x equals 3, x equals negative 4, and x equals 7. And in interval notation, it would look like this. I would have everything to the left of negative 4, the smallest value of x that makes division by 0. Everything between negative 4 and 3, the next larger value of x. Everything between 3 and 7, the next largest value. And then everything to the right of 7, everything larger than 7. Now let's talk about arrow notation. This is arrow notation here. And this is read as x approaches infinity. This is indicating that x gets larger and larger without bound. So here's the x-axis. We're talking about x just growing without ever stopping, increasing without bound, going towards positive infinity. On the other hand, we could also have x approaching negative infinity. So that's getting smaller and smaller without bound. That's going in this direction, approaching negative infinity. Now, what if there's a specific number on the number line on the x-axis? Let's say a. Well, we can say x approaching a from the left. That's how this is read when you have a minus sign as a superscript on the number. You read it x approaches a from the left, and it means you're approaching on the interval from negative infinity to a. You're approaching from the left-hand side, numbers smaller than a. So you're going this way and approaching a from the left. You can also approach a from the right, and the notation would look like this. X approaches a from the right, and that indicates that you're on the interval from a to infinity on the right side, and you're approaching a from the right-hand side. So that's the notation for approaching a from the right side. And we don't have to just restrict this to the x-axis. We can also talk about function values. So for instance, this would be f of x, the function, approaching b, and that indicates that f of x, the function values, approach the value of y equals b on the vertical y-axis. So we're approaching b from either the top or from the bottom when we say f of x approaches b. All right, now what if there is no value, no specific value of y that the function is approaching? What if the function just increases without bound? Well, we say that f of x approaches infinity, which indicates that f of x increases without bound. It just keeps getting larger and larger and larger without bound. We can do the same thing with negative infinity. So f of x approaches negative infinity indicates that f of x decreases without bound, meaning that y is getting smaller and smaller and smaller. Those function values are getting smaller. All right, so this is arrow notation, and we're going to use arrow notation now to define holes in the graph of a rational function. The point AB is a hole in the graph of the function f of x if, as x approaches a from the left and from the right, f of x approaches b. So that's written as x approaches a from the left and as x approaches a from the right, f of x approaches b. So to identify holes in the graph, or to prove that something is a hole in the graph, we can just prove that as x approaches a from the left and as x approaches a from the right, the function values are approaching some specific value b. So here's an example. Determine if 3 comma 1 over 14 is a hole in the graph of f of x, the same function we were looking at before. So let's go ahead and make a table, and let's make this table of values as x approaches 3 from the left. So I'm going to plug in numbers that are smaller than 3 but getting progressively closer to 3. So let's make a table. So the first value of x I'll use, smaller than 3, 2.9, and that's on the left side of 3. So I'm going to plug it in. When I plug in that for all the x values in here, it's going to give me 0.66. It's going to give me 0.0668. So that's what I get when I plug 2.9 in for all the x values. Now I'm going to plug in 2.99. The f of 2.99, when I plug 2.99 in for all the x values here, I get 0.0710. That's even closer to 3, but still smaller than 3. So let me get even closer. I'm going to go to 2.999. That's even closer to 3, but still on the left side, still smaller. When I plug that in for all the x's here, I get 0.0714. And lastly, I'm going to get even closer, 2.9999. And when I plug that in, nothing changes when I plug it in for all the x's. I just still get 0.0714. So it seems that as x approaches 3 from the left, all these numbers are still smaller than 3. It seems like f of x, the function values, are approaching 0.0714. Now let's approach 3 from the right side. So make a table, and I'm going to plug in numbers that are bigger than 3 but getting closer to 3. So let's plug in 3.1 and we'll get 0.0755 when we plug in 3.1. Now let's plug in a number closer, 3.01. That's even closer to 3. When I plug that in, I get 0.0719. And then I'm going to plug in 3.001, even closer to 3, in for all the x's. I'm going to get 0.0715. And last, I'm going to plug in 3.0001. And when I plug that in, I get 0.0714. So as x approaches 3 from the right, it seems like I'm approaching that same number, 0.0714. And as it turns out, 1 over 14 is that same number, 0.0714. So as x approaches 3 from the left and as x approaches 3 from the right, f of x is approaching 1 over 14. So therefore, this is a hole in the graph. I have 3 comma 114 is a hole in the graph. Okay, so what if we didn't know where the hole was and we wanted to identify where it was? Let's take a look at this example here. Identifying holes. Holes in the graph of the rational function f of x equals p of x over q of x occur when both the numerator p of x and the denominator q of x equals 0. So if we were given this question, find the coordinates of any holes in the graph of the function. Now we already know where they are, but here's how we would identify them. We'd identify any values of x that make both the top and the bottom equal 0. And there's only one value here that make both the top and the bottom 0, and that's x equals 3. If I plug in 3 for all the x's, I get 3 minus 5, 3 minus 3, 3 minus 2, 3 minus 3, 3 plus 4, and 3 minus 7, which amount to negative 2, 0, 1, 0, 7, and negative 4. When I multiply all the numbers on top, negative 2 times 0 times 1 is 0. When I multiply all the numbers on the bottom, 0 times 7 times negative 4, also 0. So I get 0 divided by 0, which is interesting because if you have 0 divided by something, usually that's equal to 0. But division by 0 is undefined. It's not exactly clear what this is equal to. This is actually what we call an indeterminate form. So the f of 3 is an indeterminate form, which means that 3 is a place where we have the whole in this rational function. We can't plug 3 in to figure out what the y value is, so what we're going to do is we're going to find a function that is similar to this one by canceling out that factor that has 3 as its 0. And once I cancel it out, I get this other function, remembering that the original function f of x cannot have 3 as an x value because 3 is not in the domain. I have to state that, but the expression that I have here actually will take 3 as a value. So I'm going to use this expression to find out where the whole is, even though the original function doesn't have 3 in its domain. So I'm going to find the y value of the whole by plugging 3 into this expression. So I plug 3 in. Basically, that's like canceling the 3 minus 3 out of both of these and just getting the negative 2, the 1, the 7, and the negative 4. So basically, that's what I get here. And then when I do this multiplication, I get exactly where the whole is. When x is 3, y is equal to 1/14. So this is how we would identify the whole if we didn't know where it was at first. We would identify what factor is on both the top and the bottom. We'd cancel that factor out, and then we'd plug the 0 of that factor into the simplified version of the expression. That will give us the y value of the whole. We have that there's a whole at 3, 1/14. Now let's define vertical asymptotes. The line x equals a is a vertical asymptote of the function f of x if, as x approaches a from the left or right, f of x approaches infinity or negative infinity. So in arrow notation, that says as x approaches a from the left or as x approaches a from the right, f of x approaches infinity or f of x approaches negative infinity. Let's take a look at this example. This function is a special function called the reciprocal function. It just takes whatever x value you give it and flips it over. Makes the numerator the denominator and makes the denominator the numerator. So it says determine if x equals 0 is a vertical asymptote of the function f of x equals 0. So to determine if it's a vertical asymptote, we need to see if as x approaches 0 from the left or as x approaches 0 from the right, f of x is approaching infinity or negative infinity. So let's make a table to figure out what happens as x approaches 0 from the left. Here's the table. So first I'm going to plug in a number on the left of 0, but close to 0, like negative 0.1. That's negative 1/10 when I find the reciprocal by plugging it into the reciprocal function here. The reciprocal of negative 1/10 is negative 10. Then I'm going to plug in negative 1/100th, and I'm going to get negative 100 as the reciprocal. Then I'm going to plug in negative 1/1000th. I'm going to get negative 1000. It seems like the closer I get to 0 from the left side, the smaller and smaller these numbers are getting. There seems to be a pattern. For instance, I plug in negative 1/10,000th and I get negative 10,000. So it seems like if I plug in negative 1/1,000,000th, I'm going to get negative 1,000,000. So these values just keep getting smaller and smaller and smaller. The pattern would look something like this. It would keep getting closer and closer to the y-axis, but I can't plug 0 into this because that would be 1 over 0, which is undefined. So it turns out that as x approaches 0 from the left, f of x is approaching negative infinity. Just keeps getting smaller and smaller and smaller. Let's see what happens as x approaches 0 from the right. So the table, I'm going to plug in 0.1, which is close to 0 but still larger than 0. I get 10. That's the reciprocal of 1/10. I plug in 1/100th, I get 100. I plug in 1/1000th, and I get 1000. So this is getting larger and larger and larger. Plug in 1/10,000th, I get 10,000. So as I approach 0 from the right side, the y values just keep getting larger and larger and larger. So as x approaches 0 from the right, f of x approaches positive infinity. Either one of these, approaching negative or positive infinity from the left or right, would cause x equals 0 to be a vertical asymptote. So I have x equals 0 is a vertical asymptote of 1 over x. Let's look at the function f of x equals 1 over x minus 3 and determine if x equals 3 is a vertical asymptote. As x approaches 3 from the left, I'm going to make a table. I'm going to plug in numbers like 2.9, and I get negative 10 because 1 over 2.9 minus 3 is 1 over negative 0.1, and that's just like the table before. 1 over negative 0.1 we said was negative 10. And for the same reason, 1 over 2.99 minus 3 is 1 over negative 100, or 1/100th. And when I plug in 2.99, I get 1 over 2.99 minus 3, which is 1 over negative 0.001, which when you take the reciprocal, you get negative 100. When you plug in 2.999, you get negative 1,000. And when you plug in 2.9999, you get negative 10,000. So as x approaches 3 from the left, we have the same behavior as the reciprocal function had when we approach 0 from the left. It's approaching negative infinity. So f of x approaches negative infinity. And when we approach 3 from the right, we make a table. We plug in numbers like 3.1, we'll get 10. We plug in 3.01 into this, we'll get 100. We plug in 3.001 and we'll get 1,000. And when we plug in 3.0001, we get 10,000. And it looks like as x gets closer and closer and closer to 3, with numbers larger than 3, it seems like the y values just keep getting larger and larger and larger, approaching positive infinity. So as x approaches 3 from the right, f of x approaches infinity. Each of these is sufficient to prove that x equals 3 is a vertical asymptote, just like x equals 0 was a vertical asymptote of the reciprocal function. We know how to find vertical asymptotes using these tables, but we don't want to have to do that every time. So there's a way of identifying vertical asymptotes without making that table. So vertical asymptotes of a rational function f of x equals p of x over q of x occur when the denominator q of x equals 0, but the numerator p of x does not equal 0. That's different from a hole in the graph. A hole in the rational function occurs when the numerator and the denominator both equal 0. But this is saying they want the denominator to equal 0, but the numerator to not equal 0. Let's look at the rational function we looked at when we were trying to find a hole in the graph. This says find the equation, maybe plural, of the vertical asymptotes of the function. So basically what I'm looking for values that make only the bottom 0 but not the top. So immediately I have to exclude x equals 3 because I know x equals 3 makes both the bottom and the top equal 0. And that we said was the indeterminate form. So Since the f of 3 is equal to 0 over 0, which is indeterminate, we know that x equals 3 is not a vertical asymptote, because for it to be a vertical asymptote, the denominator should equal 0, but the numerator not equal 0, and that's not the case here. So let's move on to the next factor, x plus 4. The 0 of that factor is negative 4. So we're going to plug negative 4 in and make sure it only makes the bottom 0. Well, I don't have any negative 4 plus 4s on top. I get negative 9, negative 7, negative 6. But here, the middle term is negative 4 plus 4, which is going to give me that 0. That's division by 0, but it's not 0 on the top. This is not indeterminate. This is undefined. And when we get an undefined rational expression like this, that's when we know we have a vertical asymptote. So this is a vertical asymptote of this function. All right, let's look at another one. Let's look at the next factor, x minus 7. So for x minus 7, the 0 would be x equals 7. So let's plug 7 in for all the x's. And the only 7 minus 7 here is that last factor. None of them are going to give me 0 except for that one. Everything else just gives me a specific number. 7 minus 5 is 2, 7 minus 3 is 4, and so forth. But 7 minus 7 gives me exactly 0. And that means I get on top 40, but on the bottom, because there's a 0, I get 0. Once again, this is undefined. And because it's undefined, I now have both vertical asymptotes, x equals negative 4 and x equals 7. Remember, we're not using x equals 3 because it doesn't just make the bottom 0, it also makes the top 0. So it's not a vertical asymptote, it's just a hole in the graph of the rational function. The last thing I want to talk about as far as the graph of a rational function is concerned on this video, I want to talk about the x-intercepts of a rational function. The x-intercepts of a function f of x are points where f of x is equal to 0. And that's not just for rational functions. That's for any functions. All you have to do is make sure that the y value is 0. They occur where the numerator p of x equals 0, but the denominator q of x does not equal 0. So this is the exact opposite of where the vertical asymptotes occur, because the vertical asymptotes have the denominator being 0 but the numerator not. Now x-intercepts have the numerator equaling 0 but the denominator not. So let's look at the same function here, find the x-intercepts of this one, and I'm going to look at what makes the top 0 but not the bottom. X minus 5 has a 0 of 5. There's no x minus 5 on the bottom, so therefore when I plug 5 in, it's only going to make the top 0. That's going to make this an x-intercept, because when I do all these calculations, I get 0 times 2 times 3 is 0, and I get 2 times 9 is 18 times negative 2 is negative 36. But 0 divided by negative 36 is just 0. 0 divided by a number that's not 0 is 0. So there I have one of the x-intercepts of the graph. If x is 5, y is 0. 5, 0. Now I already know that when x equals 3, I have f of 3 is equal to 0 over 0, and the f of 3 is indeterminate because 0 over 0 is indeterminate. And remember, when we're looking for x-intercepts, we only want the top to be 0 and not the bottom. So 3, 0 is not even on the graph. It's 3, 1 over 14, which is not an x-intercept. So let's move on to the next factor, x minus 2. And the 0 for x minus 2 is, of course, 2. And when I plug 2 in, it's going to make only the top 0 because I have 2 minus 2 here, but there's no 2 minus 2 on the bottom. I get these numbers. Negative 3 times negative 1 times 0 is 0. And negative 1 times 6 times negative 5 is 30. So when I do 0 over 30, I get that the f of 2 is equal to 0. And the last x-intercept here is 2, 0. So that's how we find the x-intercepts of a rational function we're looking for numbers that make only the numerator 0 but not the denominator.